Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss IC-741 operational amplifier and some important technical terms that are open loop voltage gain, closed loop voltage gain, frequency response, common mode rejection ratio, that is CMRR, slew rate, and an idea of virtual ground. Let's begin. IC-741 operational amplifier, that type of IC is a popular device and it is the modern integrated circuit version of op-amp. It consists of 8 number of pins. In that of 8 number of pins, from that of name 741, it is indicating that 741 7 stands for number of functional pins. 4 stands for number of input pins, and 1 stands for number of output pin. Draw that figure. Eight pins, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Pin number 1, that is offset null. Offset null. Pin number 2, inverting input. Inverting input. Pin number 3, non-inverting input. Pin number 4, negative V, that is the power supply pin. Pin number 5, offset null. Pin number 6 is the output. Pin number 7, power supply plus V. Pin number 8, which one is not connected, that is not the functional pin. Now we can integrate that IC-741 to the operational amplifier. That positive, the non-inverting input end, if we provide the signal to that of positive end, at output the signal the same phase to that of input, therefore it is called non-inverting input. Next, inverting input given to that of negative end, the signal to that of negative end, at output we obtain the signal which is a phase shift of 180 degree to that of input, that end is called inverting input. Output at pin number 6 and power supply from pin number 7 to pin number 4. As 7 number of functional pins, 1, 2, 3, 4, 5, 6, 7. Number of input pins 4, input pins 2 inputs, inverting input, non-inverting input, power supply plus V minus V. Number of output pins 1 output pin, pin number 6. What is offset null? Okay, we can understand it. As we know, if the two terminal of an operational amplifier is shorted, the output voltage is not 0. That's the important point. If the inputs are shorted but at output the voltage is not 0, for an ideal op amp this output voltage should be 0, but when we dealing with practical op amp the output voltage is not 0 when that inverting and non-inverting inputs are shorted. This deviation of output voltage in that practical op amp from the ideal value, that ideal value is 0, is known as offset voltage. That voltage we call it as offset voltage. Now that offset voltage can be neglected in case of a practical op amp by using that two terminal offset null terminals, and that can be eliminated by using a potentiometer. That potentiometer we call as trim potentiometer. Trim potentiometer means that abolish what be the unwanted voltage from that of input section. Okay, this is all about IC-741 op amp. This is IC-741 op amp pin diagram. Next, some important technical terms related to op amp. First one is open loop voltage gain. As the name indicates, open loop, so the voltage gain is said to be open loop voltage gain of an operational amplifier, that is voltage gain without feedback. For that we can draw an equivalent op amp. SC equivalent operational amplifier can run positive, negative, here is the output. V1, V2 the power supply plus Vs minus Vs, here is the output, that is the difference in potential Vd. Vd is equal to V1 minus V2. So the open loop voltage gain now we defined as the ratio of output voltage to that of different input voltage, output voltage to the difference in that input voltage. Mathematically, that is A is equal to output voltage V0 to that of difference in input voltage Vd, where V0 is the output voltage and Vd and the differential input voltage, differential input voltage. Next, closed loop voltage gain. In case of closed loop voltage gain, we can add some kind of feedback. Some portion of that of output is to input to that of input voltage. Then that type of voltage gain we called closed loop voltage gain. Closed loop voltage gain of an operational amplifier with feedback. It is defined as the ratio of output voltage to input signal voltage. Mathematically, let A dash is the closed loop voltage gain, that is output voltage to input signal voltage V of S, where VO that is output voltage, Vs input signal voltage. Closed loop voltage gain. In case of open loop voltage gain, A is around 10 to the power 5 to 10 to the power 6 value, too high. Next, frequency response. What is frequency response? How frequency play an important role to the functioning of that kind of op-amp. The operating frequency means the frequency which is responsible to operate an op-amp, that is the operating frequency. The operating frequency has a significant effect on the operation of an operational amplifier. And there are some important points regarding how that the frequency responds to an operational amplifier. First point, the peak output voltage limits the maximum operating frequency. What be the maximum operating frequency that is limited by what be the maximum output voltage of that particular operational amplifier. Another point, if that operating point of an operational amplifier, operating point as we know that is the Q point or quiescent point, that if the operating point of an operational amplifier is increased beyond a particular value for that given frequency, if it is increased beyond that a particular value, then what happens? In that particular op amp, it will achieve maximum output voltage swing, which is decreased, open loop voltage gain decreased, input impedance decreased, output impedance increased. What situation? When that frequency is increased from a particular operating point. Then these are the points we noticed. Next, common mode rejection ratio, CMRR. What is common mode rejection ratio? Common mode rejection ratio is defined as the ratio of voltage gain for the differential input signal to the voltage gain for the common mode input signal. So, mathematically we called common mode rejection ratio, CMRR, the voltage gain for the differential input signal, AD, to the voltage gain for the common mode input signal, AC. Where AD, that is the voltage gain for the differential input signal, AC, the voltage gain for the common mode input signal. Taken as equation number 1. Now, mathematically we can derive what be the CMRR for a particular op amp. We take an op amp for that op amp. This is the non-inverting terminal, that one is the inverting terminal. So, the potential here let V1, potential V2. So, the potential difference in between these two, it is V1 minus V2. This is the power supply plus Vs minus Vs, and the output V output. This is an op amp. Here Vd, and the difference in input signal, which is V1 minus V2, and equation number 2. And we define Vc common mode input signal, Vc, that is the common mode input signal, this one is the average input signal, the average input signal is called common mode input signal. The average input signal, here the input signal V1 and V2, its average. So, V1 plus V2 divided by 2. Therefore, 2 Vc is equal to V1 plus V2. And equation number 3. Now adding that equation number 2 with that equation number 3. So V1 and V2 we can get first adding then subtracting. Now adding equation 2 and 3 we get, when we add these two, V2 cancel out, 2V1 is equal to 2VC plus VD. Therefore the value of V1 is equal to VC plus VD divided by 2, equation number 5. Then subtracting, or again the value of V2 can be calculated if I put the value of V1 in any of these two equations. So using equation number 2, in that equation number 3 we can achieve the value of V2 using equation number 2. Using equation number 2 we get, so VD is equal to VC plus VD divided by 2 minus V2. In that of equation number 2 we put the value of V1. Therefore V2 is equal to VC plus VD by 2 minus VD, or V2 is equal to VC VD by 2 minus VD minus VD by 2, equation number 6. Here is the value of V1, there is the value of V2 in terms of VC and VD. So the output voltage is the combination of differential input signals plus the common mode input signal. So we can write it, the differential input signal, and the common mode input signal are applied to the input of an op-amp to produce the output voltage. That is, the output voltage is a combination of differential input signal, that is VD, and common mode input signal VC. So output voltage is now A V1 plus the A1 V1 A2 V2. What is A1 and A2? That is equation number 7. That one is an important equation where the value of A1, which is the voltage gain of that particular op-amp, provided the condition when the inverting terminal is grounded. When that inverting terminal is grounded, at that of situation A1 is the voltage gain. Similarly, A2 that is also the voltage gain of that op-amp condition when the non-inverting terminal is grounded. When that non-inverting terminal is grounded, at that of situation, A2 we called is the voltage gain. In equation number 7, we can put the value of V1 and V2 as we derive the value of V1 and V2. Putting the value of V1 and V2, putting the value of V1 and V2 in equation 7, we get in equation number 7, that is V output A1, value of V1 Vc plus Vd by 2 plus A2, value of V2 as Vc minus Vd by 2, or VO is equal to here A1 Vc plus A1 Vd by 2 plus A2 Vc minus A2 Vd by 2. Now rearranging, taking Vc as common and Vd as common, as in place of Vd it's half A1 minus A2 of Vd plus, here taking Vc as common, A1 plus A2 of Vc. Equation number 8. Number 8. Now our requirement as voltage gain AD is a voltage gain for the differential input signal. From that expression, as we know that the output voltage is the combination of voltage input differential signal and input common mode signal. So AD, from that of expression, that one is AD half A1 minus A2 and AC, which is called voltage gain for common mode input signal, this one A1 plus A2. Therefore equation number 8, equation 8 becomes V output is equal to AD VD plus AC VC. Now equation number 1 becomes at the definition of CMRR, common mode rejection ratio definition, that is AD divided by AC. The value of AD and AC are putted, that is half A1 minus A2 divided by A1 plus A2. So we obtained CMRR is equal to half A1 minus A2 divided by A1 plus A2. The expression for CMRR. Again, another expression for CMRR can be calculated in terms of decibel measure. In terms of decibel measure CMRR decibel, that is 20 log of base 10 AD divided by AC. That is the definition of decibel measure of CMRR. Therefore, CMRR in terms of decibel measure is 20 log of base 10 AD divided by AC, which is general CMRR. So what be the value of CMRR for ideal op-amp and practical op-amp? For ideal op-amp, AD infinity and AC is equal to 0. Therefore, its CMRR also infinity. For ideal op-amp, CMRR infinity. Next, for practical op-amp, as we know, AD is very large and AC is very small. Therefore, CMRR is very large. That for ideal op-amp, this one for practical op-amp, the value of CMRR. This is all about common mode rejection ratio of op-amp, the definition. Then mathematically we show the value of CMRR. Next, in decibel measure, this is the definition of CMRR and its value for ideal op-amp and practical op-amp. Next, slew rate. Slew rate is defined as the maximum rate of change of output voltage per unit time. How? The output voltage change to that of time at maximum situation. The maximum rate of change of output voltage per unit time is the slew rate. From that of slew rate, what we signify? It indicates how rapidly the output voltage of an op-amp can change with the change of input frequency. For high frequency applications, the op-amp must have higher slew rate. Next, concept of virtual ground. What is the concept of virtual ground? In electronics, the virtual ground is the terminal of a circuit which is maintained at the potential of earth without using connected directly to that of earth, known as virtual ground. So, in case of op-amp, how we relate it? Let we consider an op-amp. This is the non-inverting end, that is the inverting end, that is the output. Let we take that non-inverting end as grounded. An operational amplifier has very high open loop voltage gain, but for an ideal op-amp, the open loop voltage gain is infinite, but for practical op-amp, this gain is very high. Hence, that differential input voltage tends to 0. Here we know Vd, the differential input voltage Vd is equal to V1 minus V2. As we prefer that non-inverting terminal is grounded, since the non-inverting terminal is grounded, that is non-inverting terminal V1 as a 0. Therefore, Vd is equal to 0 minus V2. Therefore, Vd is equal to minus V2. Since Vd tends to 0, therefore V2 ultimately nearly equal to 0. Hence, the inverting terminal, although not connected to ground, but it is virtually at the potential of ground. Hence, the inverting terminal, although not connected, to earth, virtually at ground potential. Thus, the inverting terminal is referred to as the virtual ground. Now, without grounding that end, that potential also same as that of potential of ground. For that reason we call it as virtual ground. Actually that is not grounded, but that potential exactly the potential to that of ground potential. Hence the inverting terminal, although not connected to earth, virtually at ground potential, thus the inverting terminal is referred to as virtual ground. Okay. So, with the help of this video lecture we understand the concept of IC-741 op-amp, open loop voltage gain, closed loop voltage gain, frequency response. Common mode rejection ratio CMRR, its mathematical formulation, and again CMRR in decibel measure, its value for ideal op-amp as well as practical op-amp. Next, the concept of slew rate and virtual ground. So, with this useful and informative notes, let me wind up the session. Thank you.